All right. Week 6 of Shenzhen. I'm gonna start off as usual by doing a quick review of last week's pieces. We had the aquaponics maintenance robot and the remote kill switch. And I'll add any optimizations if I didn't already. I think I did mess around with an optimization here. Okay, so this is the aquaponics maintenance robot. It just moves left and right. Oh, yes. So this one here, I think I did already play around with an optimization. Okay, so this one here, this robot moves around left and right based on the signal. And then it will run feed and clean for a specified amount of time after pulsing left or right. Okay, and I think our issue here, so this one here, this accumulator tracks our position. Right? No, this is actually tracking our seconds since there was no. No. And we've got this tiny little chip here because we couldn't make room for one more line. And I think we just need to find that as a place to add, to remove a line or something here. Okay, so this loop here, we wait for data, and then we check if the accumulator matches the data. Okay, so this is the piece that does the pulses left and right then. Because once, so data is a target, accumulator is where we are currently, and depending on whether it's greater or less than, we're gonna pulse in one of those two directions, and then sub one or add one. Okay. So now the pulses. This is where we can use the gen command. So it generates just a pulse on for a certain amount of time and then off for a certain amount of time. So here in the positive case, or in the case where our current location is greater than where we want it to be, and we'll be subtracting. So first we move 0. We move 0 down, and that's our signal to move left, right? And then we sleep, and we add 50. So we have a pulse of 0 for 1 second. And in the other one, we have a pulse of 100 for 1 second. Okay, and then they both share in common this line here. They'll both sleep for 1 second, etc. I think we can get rid of this common line. So the sleep 1. Now here, instead of move 100 to x3, we're going to generate on x3 a pulse. And it's 100 for 1 second. And then 0 for 0 seconds. Right, and now in this case here, instead of moving 0 to x3, we're going to generate a pulse on x3, which is 100 for 0 seconds and 0 for 1 second. All right. It must be a simple, okay, right. We can actually just do that on P1 directly. Take out this chip. We do still need the effect of that chip, which is to initialize with a value of 50. So instead of x3, that's going to be P1. P1. Here, P1. Great, and now we have one more line of code free, which is all we needed to obviate the need for this small chip here. So we're going to have an at which means it runs only once, and then move 50 to P1. So just once at the start, we'll initialize with the default value of 50. Now we can get rid of this chip. And wait, pin's not connected to X3. Oh, this can just be P1 too as well. Cool. Okay, yeah, I'd hesitate against using gen at first because we're like pulsing it to 100 and then to 50. Or like 0 and then 50. And then the gen command only goes between 100 and 0, right? You can't choose the value that pulses to. So let's give that a shot. And it looks like it's working just fine. Okay, cool. Great, significantly cheap. Someone did it for $1. Oh, $1 less because 1 yuan less. I have a useless chip hanging around here. Okay, I could probably remove some lines of code. Let's at least see that. And let me give it. Oh. Cool. The power is near optimal, but we can probably remove lines of code, and that's probably going to happen here. Okay, so this was just handling the pulsing left and right. Now this one over here handles the cleaning tools after that. So we're grabbing data from the radio chip. There's a jump to start. Let's see if we can remove that. Because there's no other conditionals here, what we could do is actually wrap this whole thing in a conditional. And then we can remove the jump start and have sleep 1 happen here. So, if data is not 999, then we can just do all of this stuff, right? And then we sleep once at the end and loop back to the start, which no longer needs a label. So there's that. Cool. 26 lines of code. Yeah, we can still do better here. So here we move 100 to P1. Hey, Famish Integral, welcome. How's your night? Thank you, I appreciate it. That was that name was bestowed upon me at math camp. That's kind of. I wondered why I never thought of it first. Okay, we could probably do the same thing with some gens. So what does this do here? Data to X3. So we're telling X3, okay, what's in the data packet? So it's a destination. Okay, so we send a destination over, and then they're the clean and feed times. Right, so we move our data to X3, and we block and wait for X3 to finish. Then we move to 100 to P1 for a certain amount of time. This is just a gen command. And then we move 0 to P1, and then move 100 to P0. Okay, these are just 2 gen commands. You were watching Dexter while doing Microsoft Access? Microsoft Access? I haven't heard of that in ages. I can't even remember what it is. It's basically like a UI for a database-ish, right? What do you do with Microsoft Access? Okay, so here, instead of moving 100 to P1, we're going to generate on P1, gen P1, a pulse for the duration of x0, and then a pulse of 0 for the duration of just 0, I suppose. Yeah. Yeah. And then we gen on P0, x0 and 0, right? There we go. That's so much nicer. I don't know why I didn't think of this last week. Sweet. Okay, great. Now this chip doesn't actually need, what does it use an accumulator for? It only needs one register. This could be done on one chip, couldn't it? I think so. One small chip. You're getting your computer information systems degree. That's a class, you have to do it. Fair, fair. Yeah, I would too. I'd rather just write my own queries and have them saved in text. But it'd be kind of cool to develop Microsoft Access. Okay, so can this all fit on this chip? Yes, yes it can. Okay, X0 will still be our input. Instead of data register, we'll use the accumulator. And then our output to the other chip is going to be X1, X1, X1. And we're still going to use P1 and P0 for the clean and feed pulses. Alrighty. I'm just gonna delete this chip off. Okay, connect those X's, and we connect our X0 input to read. P1 still is going to bridge down and hit up the tool clean. Meanwhile, P0 still hits the tool feed. Lovely. Oh, okay, that's so much nicer. That feels good. Now we got down at 8 yuan. Our energy usage went up slightly, but we're down to 22 lines of code, which is what everyone's optimized to, except like a few really, a few people have figured out how to. You probably get it down fewer lines of code at the cost of having it be more expensive or something. Fair, fair. AI, maybe. But someone's got to use the AI. I think I'm happy with this. I don't think I need to optimize that anymore. It always feels good to come back afterwards and clean things up. Okay. And reviewing the other one from last week, so the remote kill switch. Okay, this was my design from last week. Yeah, of course. And at the end of the day, it's still good for your brain. And I know, I think our brains will still be good for something. Okay, so this remote kill switch, I was already actually pretty happy with this design, I think. Oh, right. Yeah, so this could be really small. It could just be this code here. Except that we have this keep alive thing. And that basically means we need an accumulator to count how many so the reason I have two big chips here, our accumulator on the right here is keeping track of the state of this power, and we're doing like incremental changes to it, right? Like a signal will come in to turn one of these three on or off. So we'll update one of those digits and then pass it along to this, which splits up those digits and sends it to the 3 output. So that accumulator I need to keep. And then I also need a data register because I have to branch on my input. So I need 2 registers there. And here on the left, this accumulator is keeping track of the seconds since we actually had an input. So there's a -1 input, which is a keep alive. And otherwise, the default is -999. And if we get -999 for 5 seconds in a row, then we need to kill everything. So this here has a kill everything signal. Move 0 to accumulator. Although I wonder if I can just send the kill everything signal direct to this DX300 chip, to the splitter chip, maybe. Well, we can at least do some incremental changes here. I think this can be a lot smaller. So let's just look at where we're at. Okay, yeah, I think I did find something better. Okay, so the rough idea here, we bring in our data and we branch on that to either go test if we're at 5, or we fall through to interpreting that signal as a toggle. Okay. I think we can do this incrementally, so we jump to test, add 1. Because there are bits of code here that are duplicated, right? So there's the whole resetting, move 0 to accumulator. That all happens here. Basically, that move 0 to accumulator should only happen when we're not -999, right? And what's this move -1 to x3? Oh, right. Is that the kill signal? You're right. I think I could basically move all of this up to here. If I can chain this conditional, right, instead of having a jump test here, let's have a, let's just do the test right away. Test equal accumulator 5. And then this line here is no longer test. This is going to be the reset, right? Okay, and then we jump to reset. Right, so that should still work. No. Um, let's add a little breakpoint here and see what's going on. Okay, so we have -999 coming in. Oh, our accumulator's at 0. So we haven't already been adding. So I'm going to go back here to our very last -1 and see what's happening there, why it gets reset. Okay, so this is all normal. And now we have a -999 come in, and this should increment, right? So we found that's equal to -999, so we increment. We're testing if we're at 5, and we're not. So we end up doing this. Oh, right. The whole point of doing this was that we only need to move 0 in the... So moving 0 is essentially the reset. And there are 2 times when we reset it. Like every time we get something that's not -999, we reset it. And once we get up to 5, we reset it. Although we don't actually need to do that when we get to 5, do we? So I can delete this line here. And then now, it's only when it's not -999 that we reset our counter, right? We add 1. Oh, this is so simple when you think about it this way. So we look at our incoming data. If it's -999, add to our counter. Otherwise, set our counter back to 0, right? Yeah. Cool. And now this reset doesn't even need to be a jump anymore. We can just do that right here directly. So we're going to do move -1 to x3. And we instead jump to end. I'm doing way too many edits before a run. So I'm just going to give that a run, see if that works. Okay, there's a breakpoint. Okay, let's check our breakpoints again here. So this should be 0 because we have -1, right? So the next step, -999 is coming in. We should just be incrementing it. So we add 1. There we go. Test that we're 5. We're not 5. Ah, yes, right. Chaining these equals ends up doing that to us. Oh, you know what we can do? Let's just move this negative right up at the top. Negative, so move 0 to accumulator. That way we don't accidentally fall through to it. Great. There we go. We fixed it. Okay. Yeah. It still kind of breaks my brain the way you can't like chain conditional, so you have to think about stuff like this here. Okay, so this jump to end here is no longer necessary. This toggle, we can use a label. We'll make a comment. Okay. So if it's not -999, then we try to well, we try to do a toggle here, which means we move this 0 here as our signal that it's a normal thing, right? And then these 2 bits essentially are all we need to switch the state of this triple here. And my thought here is that we can shrink this chip down if we don't need to check the value of the data register, right? If we can always just be in the 1 branch. is that we might, once we send a new toggle signal over here, it's going to be toggling from something that's not 0, and it needs to be toggling from 0. So like this accumulator does need to be set to 0, right? We can't just bypass it and set this directly because it will still remember whatever that previous state was, which is not good for us. Let me clear these breakpoints. I just want to give this a proper run through. Okay. We can probably shade more lines of code somewhere. And there's some code that's running more than it needs to. This test equal 5 is running suspiciously often. No, I suppose not. This reset here is not running very often at all. Oh, that's weird. No, this reset here is running often enough, like as often as we're not adding. That's fine. Maybe that doesn't need to be a reset though. Or like, yeah, that's running more often than it needs to. Because it only really needs to run. Well, we could have it run once it hits 5 seconds exactly. Right now we just have it run. Anytime it's not negative 999. But then that goes back to recomplicating the design of this. Test-free quality is reasonable. It should happen as often as the add one, sure. Right, this move 0 to accumulator hardly ever happens. And we still have the cost of checking it all the time ago. And I wish I could send a multiply signal. That way I could be like multiply by 1 or multiply by 0. I guess I sort of kind of have essentially that with this branch here. But it does require that I use move x0 to data. Oh, right. This is why this is happening. This is why we need the second register. Because we can't use... We can't get two x bus values at once in the same instruction, right? Otherwise, we end up with this sleep locking thing. That's why this needs a data register. So there's actually not really a great way to get rid of that, is there? Yeah, we have to get an x bus value, save it temporarily, and then get the other x bus values, so x0 here and x0. And I remember like I had some hacky workaround for that, so I didn't have to use data register, but then it just costs more. It costs another chip. Probably costs energy. leave a comment here. This is the actual reset signal. See, I could have the move 0 to accumulator be here. Move 0 to accumulator. Right, and things should still work fine. If I comment that out. Nope, we broke something. We start killing things too soon. Right, because the keep alive, when we have the keep alive signal, I could have it set only when I get the keep alive signal -1. Do I set to 0? That should, yeah, that should drop my costs a lot. But then what if we never had the keep alive signal, right? What if we just had a lot of kill switch signals? Then in that case, we'd be kind of screwed, right? So we can't do that. Yeah, I think we kind of do just have to set it to 0 whenever we get something that's not -999. Like if there's a way to do that, I'm missing it. We don't actually need a start label. Okay. I think that's at least a little bit cleaner. But that's as clean as I get here. We can't really downsize unless we drop yeah, we just need those registers. Someone's figured it out. I mean, I suppose I could drop the cost. Oh, I could drop the cost by doing this bit here directly. I don't need this DX300. I do have the real estate on the second big chip. And that just adds so many lines of code. So I don't really want to do that. I like my design. Okay. I'd have in mind to like realign everything here, but I'm not gonna mess with that. Okay. I'll live with that. Well, time to go on to something new then. Smart grid control router. Okay. Control router important from Wooly Lee. Okay, I'm pleased to say we have been selected for another Sunhausen project, a simple data router for smart grids. Mr. Sun was never interested in civic infrastructure before to my knowledge, so I wonder what he's planning. I may ask around. My uncle has had dinner with him once or twice. We can do it. Note these XBus inputs are blocking, so we will need to connect all inputs so they can be read at once, simultaneously. I'm not sure what that's about, but I'll keep that in mind. Was this remote kill switch the Sun, the other project? No, it was the aquaponics that we got from Sun. Yeah, we're getting like actual serious projects now. Cool. Yeesh, what's this? We have a meter in and meter out. They are X bus inputs and outputs that connect this node to building smart grid power meter. Okay, that's here and here. Cool. Lower in and lower out are X bus inputs and outputs that connect this node with a lower ID number. Okay, so it connects to other nodes. Higher in and higher out are X bus inputs that connect to a node with a higher ID number. Okay, and the first value in the data packet is the ID number of the destination and indicates how the packet should be handled. Okay, so data packet has how many? Oh, wow. Like 6 signals or 6 data values, sometimes 5. Well, it depends on what's coming from. Okay. So we have, if our ID is less than meter ID, ID being what? We transmit data to the lower node. If it's greater, we transmit back to the higher node. This kind of makes me think of TIS 100. And if ID is equal to our meter, then we transmit data packet to our meter. Okay, the local ID number of the node is stored in a secure identity chip that can be read as an XBus input. Okay, so this is our ID. The second value in the data packet is the length of the rest of the data packet. Ah, okay. We'll need to store that in an accumulator and like decrement as we're reading from in a loop or something. The ID of the destination. Okay, so that comes from what meter? What's up with higher in and lower in? I guess we can get a value from any of these. Oh, right, that's what they were saying in the email, right? These XBus inputs are blocking, so we will need to connect all inputs so they can be read at once, simultaneously. So they're all read at once. I'll need to look at this. Okay, so we try to read all 3 at once, right? And we realize, okay, we're not getting anything from higher in. Okay, so we're blocking on higher in and meter in while handling lower in. And in this case, lower in, it says, I wonder what where's our ID? So 4, there's 4 data packets and that's being sent somewhere. And that's actually our ID. So 596 is our ID. So we just send that right back to meter out. Makes sense. And then we get meter in. Similar thing happening here, except that goes to a lower ID. So we send that whole packet down to a lower. Okay. Gonna have to really think about how the blocking works here. So suppose let's connect these all to one of these. Meter in and lower in. And maybe we connect this to something else altogether, right? And what we have to do here is basically choose a data packet. So we can't like sleep waiting for one of these other signals when we've got lower incoming. So how do we determine like which one's the first to come in? We can't like sleep on all 3, can we? Mm. They are all blocking. If we block on one of them, okay, let's suppose we just had two signals here, right? And we want to handle whichever one comes in first. How do we erase that here? The moment we try a read, we're blocking. Can we? We can't combine those on the same wire, can we? I guess we could. Sleep on X. Maybe. Let's look at that. So this is going to sleep on X0 and move X0 to X3. Very simple. Wrong. But like I want to see. So we're basically always reading to meter out. Or writing to meter out. Wait, what values even are these? So in is doing its thing, but why is out going to multiple? It should all just go to meter out, right? So first thing we do is correct. The second thing we do, oh, it's wrong in two places is what it's saying, because we didn't do meter in. But we did do lower out. I see. Cool. So we can just combine those in a wire. Let me just see this. Can we combine an output wire as well? Okay, cool. In this case, oh, look at that. Look at that. So in this case, higher kind of took priority. Higher read that, and there are not two wrong error bars here. Which is odd, because like in this case here, like meter in, so meter out, you were supposed to get meter out, right? No, we're supposed to get lower out. Right, higher always takes priority. No matter what. I see what's going on here. Okay, so we can share inputs, we can combine inputs. We can't combine outputs. Okay, so, great. The output doesn't matter. The output only depends on what the values are. It doesn't matter which input does this. So we've solved that problem here, right? We can just sleep on X0. We still have 3 outputs here. So I suppose we can do this with 2 chips. Right, one chip is also connected to the code. And I could send a signal over to the other chip, which is, let's say, like, which chip we are sending, we're going to send out to. But what's going to happen is we're going to need to like store that, like the chip we're going out to. We're going to need to store that in the register. And I imagine we could have a loop, but the loop's going to end up having to check that register on every loop. So that's one register just gone. That could be our data register in a big chip. And then I suppose the accumulator can have our like remaining packets to send or something like that. There's always gonna be those first two. And then we're gonna connect. How do we wire this? Let's do it this way. I'm gonna wire it semantically. So x3 is our higher out, x2 is our meter out, x1 is gonna be our lower out. I don't think we need a bridge. And then x0 is gonna be our input. Whoops. And the reason, like, I have to split this between two chips because no matter what, we have three outputs, yeah? And then we have two inputs essentially, so it has to be split between two chips. But what I could do here. So this reads the ID from there and moves out to x0, moves out to the big chip. And x1's just the input. Okay, the local ID can be read as an XBus input. Great. So we're gonna sleep on x1, right? And then when x1 comes in, we're gonna compare. So let's move x1 to accumulator and test compare with x0. Our accumulator with x0. And if it is I think our plus case mean, let me just look that up real quick, our TCP. A is greater than B means plus, okay. I think I want to compare the input, so x0. So the first thing is the ID, which we move to the accumulator. So we're going to compare the ID with our ID. Now, if the incoming ID is greater, then we're going to send a signal over. We'll send 1 over to the other chip. Move 1 to x3. It can just be like 1, 0, and -1. Otherwise, move -1 to x3. And then otherwise we move 0. I think otherwise we can move nothing to x3. Right? Like here we can sleep on something, and if it's negative, then it's telling us to move left or right. Something like that. I think I shouldn't use 1 because a positive number could be an ID. I'm gonna assume that negative values are invalid IDs. Okay, so our positive case then will be move -2. Our negative case will be move -1 to x3. Okay, and we are running out of space. We might need 2 big chips. And then now in either case, we're going to move the accumulator over to x3. Then we're going to move x1 into the accumulator again. And read a certain number of packets, and then we do our loop. And we pass all those packets along. Okay, this goes into a bigger chip. I'm just going to connect them both for now. We can rewire things later. Okay, I'm just connected so it's happy. Okay, so now we move our x1 to the accumulator, and we have a loop. And in this loop, we're just going to move a value over. So every time we're going to move accumulator over, oh, well, no. I suppose we move x1 into the accumulator, and we're going to move that value over. So move accumulator over to x3 as well, right? Okay, so in our loop, we're going to end the loop when our accumulator is 0. Right, so in that case, we jump to the end. Otherwise, we just keep moving values over. So move x1 to x3, and we subtract 1 from our accumulator. Cool. And I suppose you have to jump back to the loop. If I could put that condition at the end, the data packet's always going to have at least one value, right? It'd be silly if it... Yeah, it'd be silly otherwise. So let's rewrite this. We're always going to move x1 to x3 and subtract 1. And we're going to test if the accumulator is equal to 0. If it's not equal to 0, we jump back to the start of the loop. Jump to loop. Okay. Cool. And meanwhile, this thing, I'm going to put this in the data register because you don't actually need to do any math on it. This thing being the ID. Right, we're doing some comparison against it, but that's it. And based on the comparison, we send a value or nothing. We send no value. Right. And when we're done, we move that ID over. And then we move the packet length over after saving it. Because we need to increment that or decrement that packet length in this loop. And we don't actually need an end here because we'll just jump straight to the beginning, which starts with the sleep X. Cool. I think that does what I want it to do there. Okay, so let's rewire things here before we move on. Can we... just cram that in there. So x0, and then that can still be x1. And our x3 can connect to the x0 there. Okay, and then these three still connect to the three outputs. Geez, I hope I have enough space. It's gonna be a pretty similar loopish thing. So we're gonna sleep on x0. And basically, if it's less than 0, well, first let's move x0 over to our accumulator. Or rather, yeah, well, let's do our accumulator. Nope, we're gonna use our accumulator in a loop later, so let's move it to a data register. So we're gonna move that x0 to a data register. And we are gonna check if it's negative. So test less than, so test that data is less than 0. And if it is less than 0, we leave it in there. We're fine. Otherwise, if it's greater than 0, then it's actually an ID. Well, we're going to move 0 to data because data is going to be our case, our like switch on this here, right? So we're going to move 0 to data in the negative case. But now this is already handling, well, no, the positive case. In the positive case, we just move, no. We don't want to move 0 to data because that's the ID. It needs to go out. So we're going to move data out. Well, hold on. I think we'll have to temporarily use our accumulator. Okay, so our accumulator, let's try and make that be our ID. So we'll, in this negative case, right, this is a case where it's not negative, right? This non-negative case. We're gonna move data to the accumulator. Oh. No. Let's just use a data register. We can switch things around later if we need to. We're gonna move 0 into the accumulator. And 0 is going to be our switch case thingy. No. We're gonna move 0 into our data. We're gonna move 0 into our data because we already moved like our switch case thing into data. The either -1 or -2 when we did this first move x0 to data, right? But in the true case here, when it's true, then the thing we've moved to data is not the ID. And we'll need to move x0 over to accumulator. Now, accumulator has our ID, right? We need the same thing here in the false case. So we're gonna move data over to accumulator. And this is, we'll say that's an ID. Otherwise we move an ID over. Great. So after all of this is said and done, we have our ID in the accumulator, and our data is our switch case kind of thing. So in any of those cases, we move accumulator out to, well, it depends. It depends on our branch. This is where it gets tricky, because we do need to move the accumulator out before we even get the next value. Like the next value we also want to store in the accumulator, it is our packet length. We basically kind of already need to start our loop. What if the main thing in our loop is always moving? So like we always branch on data. Like we're gonna have to branch on data right now. And then there's like a special first case here where it turns out the accumulator has the ID. And then in subsequent cases, the accumulator will actually have the packet length. And then we're always branching on data. I don't know, like maybe we should be sending this to 3 separate ships. Maybe that'd be like an easier approach right now. Like, where's my branching here? My branching here is to move -2 or -1, right? But instead of that, we could just like be sending it off to another, like, our main loop always has move x1 over to x3. Maybe we need a dedicated small chip just handling. Like the routing instructions. But then like that needs to be passed along everywhere as this like -1, -2 switch case thing. It'll need to be passed on to every other ship. Unless we branch into other ships right away. Except, so we can't even branch to the 3 outputs because what we only have like 2 more outputs here, right? We're already using this and that. Okay, so let's just look at what this switch case type logic looks like. So we basically have like a test equal data is -2, right? And in that case, that's our positive case. We'll say higher, and then -1s are lowercase. So in our higher case, we'll move accumulator over to x3, right? And in our lower case, well, we need to test that. Test equal data -1. You don't really have a proper, like, if we had a command that was like jump relative, like you can just jump to a line where you can input a line, or you can pass like jump length as an argument, or pass an address as an argument, that'd be great. but this assembly is constrained not to do that. Move, so -1 is lower, right? So move accumulator to x1. And otherwise, we move accumulator to x2. And it's going to be, I know the result of test equal x0 or accumulator. Wait, sorry. Beta equals 0, right? So those are 3 cases in the loop. It'd be nice if I could use the same code for everything. But see, in this case here, the very first time we're doing it with the accumulator. We're passing the accumulator along because it has the ID. Ideally, we are just doing this generically on x0 and doing that in a loop while accumulator goes down, right? So in the general case, this will be x0. So like maybe what I should do is not send over this ID yet. We just send one like control bit to be sent saved in data, which means there always has to be a control bit. Like this code here needs to handle sending over the 0, right? We're manufacturing a 0 over here. By like assuming like if it's positive, oh, there's an implied 0. And I'm thinking I don't like that. So we can remove these lines here. Thing is, the first thing is still the ID. So the first time around, what if we send over the packet length twice? Or like we send over like an incremented packet length. Move x0 over to data. And then move x0 over to accumulator, right? So this is going to be like a larger packet length. We're not going to inspect the packet length mid loop. So this loop can just be generic there. So this is a, we'll just comment that as len. Okay, and we'll have to send over a manufactured length to this chip. Great, so we have those 3 conditionals, and at the end of that, we subtract 1 from our accumulator and test equal accumulator to 0, and if it's not yet 0, we're going to jump back into the loop. Great, so our data is our like switch. We'll call it case. Okay, now over here, these 2 kind of need to jump afterwards. And if it was disabled altogether, so in the turn, I suppose they could both jump past after as part of their thing. Otherwise, we move 0 over. I don't know what that's doing here. There's gonna be too many lines of code. Send like an incremented accumulator. And we kind of have to do like a look ahead. So move data to x3. This is like our ID that we're moving along, right? Then we move x1 over to accumulator. This is our length, right? So we send over the higher signal, we send over the ID, we send over the length. What we should be moving, and what we want to do here is move the length over. Yeah. I am pretty tired. I might end up needing to call a night early here. Well, hold on. Let's try an alternate approach. Let's wire it up and see what it looks like. I won't go too far into it, but like, what if you just have 3 separate chips here? And this chip here is just choosing which chips to send to. And we just send everything along. Geez, this would be a little bit easier. Would it be easier? I feel like it would be easier if the packet length was sent first. Then to do a loop. Yeah, you have to do all this stuff before the loop and then do the ID. This here is nice if we could, if setting up that niceness didn't make things messy here, right? Let me try something else here on the side. Okay. So either way, this little loop here, it is nice and small. This sends everything past the packet length and the ID, right? So before that happens, we should send the ID and the packet length over somewhere. Man, I wish you could save an address to a register, like a destination to a register, right? That way we don't have to branch. Because this loop here is tiny now because it's always sending it to the same thing. But once you have a switch case, then it becomes big. Like that. Actually, suppose we have like just 3 chips and one chip decides if it's even running at all, like based on its condition. It just checks its one condition, because right now we're doing this ternary condition here and it turns into a switch case. If everything just had binary, I'm looking for my case, it's my turn to run, right? But some chips still needs to like read everything, I guess, in order to decide that. Let's still take this out. Let's try wiring this up, see what this kind of a thing looks like. And we can do 3 of these. That seems so expensive. I'm sure people have less expensive solutions than this. But maybe we start by getting there. If we do something expensive that gets there, we could maybe see the structure from there and be able to simplify it. So in any one of these cases, it's going to be I could have one chip reduplicate the ID and send it over to all three of these. And like the off case, they're all just sending to, like, passing on to null instead of passing it in. Well, no, we don't want all three of them to do the comparison against this, do we? Well, I suppose that is our implication. See, I'm not even sure how this would be wired up. Because this just defers the problem where we don't have 3 additional outputs here, right? So each of them could have like one input saying yes or no, go now. And one chip just says that. And then they otherwise have if we do this, we so something like this, right? The first input x0 gives us the yes or no, and this x2 gets sent to multiple chips. Can we do that? Well, it can't get a yes or no, because then this thing would have to give a different signal to everything else. We have 3 different chips compete. Basically what we're getting at is, like, can we have 3 different chips compete for this? And no, not unless you like triplicate the signal and send it over to all 3 of these. And we can't triplicate it if we don't have enough. I suppose if they are all maybe they can all read from, like, say this here, and then some chip here could triplicate the signal. Yeah, no. I might have to sleep on this one. Does it make sense for this chip to, like, send it over to 3 other chips? Send, like, the same data to 3 different chips. As soon as any single one of them, they're all going to race, right? They're all going to race to read. And as soon as any single one of them reads, then that data is not available to the other chips, right? We saw in our test earlier what happens when you split a wire into 3 different outputs. Give me a sec here. I've lost my... Okay. Yeah, I don't like this. I think I have to go back to the other design and try to salvage that one. Because this is otherwise like... I mean, we can have a very little dump chip, small dump chip, actually. It just sends these values to all of them, and all of these are connected to this. So they all have access to the ID, right? But we don't even have room to wire it that way. Which is just as well, because we probably shouldn't be doing that. Like, we could bridge that. Nope. Is there another? There's just no. There's no room. Yeah, 4 chips is too many. Let's go back to the other design. Difficulty here. So the reason I decided to front load with the packet length over here in this chip design is that before we get to the packet length, we have the ID. And the ID is going to have very similar branching logic here, and that's going to be duplicated. Very similar, but not identical. And like one way to make it identical was to have it all be generically treated in one big loop, right, where we get the full packet length first. I'm just going to duplicate off of this, where we get the full packet length first. If we do that, yeah, this becomes easy. But if we don't do that, is there still a way to keep similar logic? Not really, because you have to do it once for the ID. Right, you branch once for the ID. And then you branch a second time inside the loop. Because between those two, you have to check the accumulator. Or you have to like load the accumulator with the packet length. Hi Albie, welcome, how are you? Jeez, this is a tough one to fit in these chips. Like maybe I split this between 2 chips. I could handle the ID separately and handle the packet itself separately. But then now, like, wiring that's a nightmare because both those chips have to be connected to these outputs. So like broadly structure-wise, splitting between 2 big chips makes sense, right? You can't just have one chip just by number of inputs and outputs. And if this one here has to output to those 3, oh, I can't see that in Albie's profile. Hey, Zeno, how are you? Oh, no fair. I'm super tired too. I was thinking I might actually be short today. But now I've got this problem here, which has me in a little bit of a bind. It's a tricky one. Like conceptually, it is simple, right? You have packets coming in, and from these three XBus inputs, and then you send them to one of these three here, right? So in order to know which one to send it to, you have to compare the first element against yet another XBus input here, right? So you compare the first element against that, and then this second element here tells you the length of the remainder of the packet. And now that has me in a bind because like you branch on the first element, right? Like you might send to higher, same, or lower. And then this accumulator allows you to start a loop to send the remainder, and the remainder will all have to follow that same branch. But we only have room for one branch, really. So the tricky kind of thing I'm trying to do is figure out how to have a generic loop that will also handle the ID. Oh, you can't also handle the ID there because the first time through the loop you have to get the ID. The second time through the loop you have to, and you then have to like save the length of the packet so that you know how many more times to increment the loop. All right. This is a tough one. Move, maybe like I can use those, you know, these @ symbols here, where it's like run this thing only once. So I could have it do all of this, where we assume like the accumulator has the ID, like the first time around. Or no, sorry, the accumulator is what? Our data is our branch here. And our accumulator is the length. Move accumulator over to x3. Right. Accumulator was my code from earlier when it's like the first ID was stored in an accumulator. Data is already storing our branch. But after the first time that happens, where we move x0, let's say we move x0, and that's going to be our ID, right? And after all of those branches, we can have basically some sort of move data, or like move accumulator, move x0 to the accumulator. But we move it to the accumulator, and then we're not... We move to the accumulator, and we also have to move it out to the branch output. I'm supposed to create my own sort of relay modules, which delegate to the correct inputs. That's the thing. So I've been thinking about like different ways I could split this up. Right. This here right now is from an idea I had where like, what if I front-loaded the packet length, and this was just a dumb thing. And instead, first I sent over our branch signal, right? So that's why this is a accumulator. First, we send over our case, and then this would handle everything generically, right? It wouldn't have to stop halfway through and look at the packet length. But in order for that to happen, the first chip basically needs to look ahead to the second element, and pass along the case and the incremented length. Well, first it needs to pass over the case. Well, yeah, the case, the incremented length, and then it needs to repass the ID, which was used to get the case in the first place, and then the normal length packet, which needs to be saved, like the value before needs to have been saved. So that's not great. Right, I suppose I could have multiple chips coordinating in order to give myself more room here. But the thing is, there's not even really room for more chips. I think it essentially has to be done with 2 big chips. So like this could be my dumb relay module. I had another idea where like I could have 3 small chips and each of them just waits. And if they and then passes everything along, right? Like it waits for its condition. It's constantly comparing the ID against the first case or whatever. But in order for that to happen, you need to like triplicate the very first element, which is the ID, and pass it along to each of those before passing along all the elements for someone to take. Right, and who takes that is whichever chip decide, okay, this is mine based on the ID. But I think that kind of idea was here. That doesn't even really work based on wiring. We could try be fancy, but it's also expensive. Like the fact that it barely fits on the board makes me think that like this is probably a non-starter. But basically each of these would have the same code, and as their x1 is used to compare the first thing they get out of this x0, which is going to be the ID, right? So the very first thing, we're going to like sleep x on x0, test compare x0 against x1. I don't think we can actually do that. I think we have to first move x0 to accumulator. No, I think we can do that. They're from different sources. And like in the neutral case where it's not greater than or, well, here's the greater case. So x0 coming in, x1's our ID. So if x0 is greater than, right? So in this case, we're just gonna, in a big loop, move everything over. Otherwise, you go back to sleeping on x0. And I don't think this would even work because like this might be greedy, right? Like maybe sure all of this falls through. Like this is the loop code or whatever. But then if it follows through all of that and goes back to the start of its loop, then it might greedily steal from things that that these other two chips were hoping to get. And then that still has a problem where, like, maybe there's salvageable ideas in here. All right, so we can combine these inputs here. Like this chip would have to send. It takes the first packet, triplicates it, and sends over x1, x2, x3. Actually, what if it just sends? Nope, it'd have to send each of those individually. And we can't do any sneakiness of like combining wires or something, because then these will greedily compete for those. Right, there's just not room to like have a branch going that way. So the fact we can't even wire this tells me like this is probably a non-starter. So back over here, I suppose. Yeah, where we're gonna abandon. We're gonna abandon this idea here. The first thing's always going to be an ID. You know, we wouldn't have to send things over. So if this thing is doing the delegation, like all the branching, whatever, like one or the other chip's gonna decide. So if this chip does the decision, it's gonna have to send the case enum over to this big chip, this other big chip on the right. Or this thing does that decision itself. The thing is, I've said like the chip that makes this decision can't also be the chip that sends everything out, because there simply aren't enough outputs. What if I hijack like a P1 input here? So if we were to take this and connect it to a tiny chip, that just converts it. So a normal chip here. Yeah, so sleeps well, we're just gonna move x1 to p0 and sleep for 1 second. Like maybe that simplifies things enough. That we can always just test against ID. The obvious fear is that this simply won't be long enough to handle that. Wait, I was working on that. Okay. So in this case here, we sleep on x1. There's this test comparison. The test compare, instead of being against x0, would be against p0. So we sleep on x0, right? maybe we can squeeze this in here. Like we were able to squeeze in this logic here, right? But this loop will be longer because it will have the branch. I don't know, we could at least start coding this out. Having a solution that's too long to fit on one chip would mean we at least still have a solution in mind, and we can mold that into something that fits, right? So let's compare this against P0. So compare incoming ID against our ID. So there's a plus case, there's a minus case. And in the plus case and minus case, we essentially would put into data our branching code, or our branching enum. So move we're gonna move x0 over to our accumulator, so this being our ID. So move -1 to data, otherwise move, wait, in the positive case, we're gonna move +1 to data. Or you know, we can just put in the names. So 3, because it's gonna go out to x3. Move 3 over to data. We're gonna move 2 over to data. No, the negative case is actually 1. 1 over to data. And in both cases here, we're gonna jump to our main loop. So jump to loop, jump to loop, oops. And otherwise we move 2 over to data. Okay, I think this... So this is obviously not going to fit, but this is going somewhere. This at least... I think this actually allows us to front load. I don't know what... Let me just look back, because I don't know what was wrong with this. The issue here... Oh, no. This isn't even the code. I don't have a saved version of what I was trying earlier. But I'm going to go back to that idea, because it's seeming like it could work here. So... So we'll have 1, 2, and 3. That can be the first thing we send over to a chip. So this is still gonna sleep on x0. We'll handle that later. But basically we could have a chip in here. x1, x2, x3. Right, so we're gonna sleep on x0, and in this case, our first x0 is going to be our little branch code. Right here, it's just looking at the ID and choosing the enum. So we could have a small chip do that. We're not gonna do this way, because that's gonna be over on the left somewhere. Try to keep as much real estate as possible. So we're gonna move x0 over to our data, and then we'll have our loop. And it's essentially gonna be move x0 over to accumulator. On everything. It still needs to handle the first thing. Geez, we need a tiny little bit of code that routes the ID before we look at the second bit. Okay, so x0, move that to the accumulator. This is all going to be reloop initialization code. Okay, so this is the ID. And then now, based on that, so test equal data is equal to 1. We're going to move our ID to x1. Otherwise, if that fails, we're gonna test equal. I don't think we want to chain them that way. We'll just do a test equal data equals 2. Move accumulator to x2. Test equal data equals 3. Move accumulator over to x3. We're running in circles. We're running back sort of into the same problem. This is sort of like a function. Maybe we treat this like a function we can call. But the thing is, if we move, we need another register if we're gonna treat this like a function. Because like we'll need a register to pass in. Or like we'll need to like duplicate the packet that we're checking, because this can't just be like move input over, right? It's always gonna have to be like move x0 over to the accumulator, which like that will override our accumulator needs to have our loop. We can't save anything. Right, like we can't inspect incoming data if our accumulator must be reserved for the loop count, the length. But you know, this is not so bad. Like the ID is always positive. It's not so bad that the loop thinks that's a loop length. And you know, in the first time of the loop, we're basically like move accumulator. We move x0 to accumulator. This is actually the packet length. And then we stop moving these into the accumulator and we start instead moving the x0 directly into the other side. How do we get away from having to inspect the first two values? We just need to inspect the second value. Right, if the first value that we're getting is our enum case. If the first value that we're getting is our enum case, I think my idea here is to duplicate the packet length value, because then we can have this be generic. We don't need to write over to the accumulator. I mean, the first time through, we can write to the accumulator, sure. That's gonna be the ID, that's gonna be big. That's like our resets. So like, but if that's the case, then we also need to duplicate our ID that we're sending over. So move x0 over to data. So data, yada yada. So we're always going to be moving x0 over to x1. We move x0 over to x2. We move x0 over to x3. And after all of those, we subtract from 1. Then test equal our accumulator. Check for our accumulator is 0. If it's not 0, we jump back to the loop. Okay, and the only thing that this is missing is setting the accumulator. Now, the first time we run through this loop, we are moving this x0, which is the ID. So the second value here, before we do this sub 1, or like after we do the sub 1, the second value we're getting, which we can put an at in front so it only runs once, this value is the packet length. So we can move x0 over to accumulator. If our packet length is duplicated, then the next value that we're moving over, the next time we get x0 in our loop, is also going to be that packet length, and it's treated just as data in that case instead of an instruction. And now, of course, we'll also actually need to add one, because we've added like an extra piece of data. So add one, so that we also handle the next length value. So this chip here can work. Now at the front of all of this, I don't know, we're gonna like move 999 over to the accumulator, or 99 over to the accumulator. That way we don't accidentally like end up ending. This is kind of our reset here. Okay, so if we send over to this chip, just first the analysis, the enum case, and we manage to send over the packet length twice, then we're golden. Okay, so this one over here does exactly that, performs the analysis. So it moves either 3 or 1 or 2. Except it's not going to move that over to data, it's going to move that over to x3. x3, x3, x3. Let's compare accumulator against P0. No. we're gonna compare that against x0. So we're gonna sleep for x1. We'll make x1 our input. Sleep on x1, which is our ID. We'll temporarily move that to our accumulator. And then we compare that against x0, which is our ID. And then move one of those three values over. Great. Then once that's all done, we have our loop. So the first thing we do, the accumulator has the ID. So first thing you do is going to be to move accumulator over to x3. And then we need to move the length over twice. So move x1, the input, this is going to be the length, over to the accumulator. Move accumulator over to x3. Do that twice. And then now, oh, is this going to fit? It could fit. And then now in this loop, we're just moving the rest of x1 over to x3 while subtracting 1 from the accumulator in the whole rest of the loop. And then we have to jump back to the loop. We need one more line of code. All right, I think one more line of code and this works. I suppose we could split this off into another chip. Right, I could have a chip whose only job is to duplicate the packet length and then pass it along here. It would work. It'd work, but it's not satisfying, is it? You know, it's good to at least pass. You're right. Let's get to a passing state. So instead of reading off of x1, then we'll read off of x2. Okay. And then now this little tiny chip over here so we're gonna sleep on x1, then we're gonna move x1 over to x2. Right, so we can delete this line. Oh wait, hold up. No. That's not gonna work because this chip also needs to interpret that packet. Well, hold on. Like this needs this still needs to move see this line? Move x2 over to the accumulator. And then move accumulator over to x2. Well, that's right, that's not consuming it. How does that work? So over here, we get our first length. So let's say this thing duplicates it. We get our first length, and we save that, and then we pass that along to the other chip once. Then we'll go through the loop. The next thing will be the second length, and we'll just pass that along like a data value. So this does end up getting 2 of that. I feel like, though, this is going to happen off by 1 because it doesn't know that there's an extra value yet. So actually we have add 1. Yeah, so as soon as we save the length, we're going to add 1 to it. Add 1. Then we're going to move accumulator over to x3. Cool. No. This is sending over. Let's take a step back. The whole reason we're doing that, we needed 1 more line of code. If we're doing that, that doesn't help. Like, okay. So I'll take a step back here. This x2 length. Jim the Dandy. Welcome. I'm not sure I get your meaning though. Okay, so this we save the length, we pass that length along. And then we have our normal loop where we just move x2 over. Yeah, we move all the remaining values over and subtract, and we have a test. We run a test that our accumulator is 0, and in that case, we jump back to our loop. So if it's not 0, we have negative, jump back to loop. Okay, you would still need 1 more line on top of that, right? So this thing wasn't duplicated. So the goal for this chip was just to, this one performs analysis and gets our little switch case, 1, 2, 3, right? And it passes along to this chip, so that this chip can just save that. So it saves all that space, just 2 lines of the code to have our enum, right? And the issue we ran into that here was like, this still does need to look at that second like, yeah, it's going to branch off of that, but it still needs to look at that second value to know how long to last. So I thought, I was like, what if I don't know. Like, what if we had a different kind of preprocessor and it just told us 99 to accumulator. So what this is doing is after the first time it moves something over, it moves an ID over, then it also moves the accumulator, then it stores the packet length in its own accumulator, and then continues with the loop. Which is why it wanted that duplicated. Oh. Because if it's not duplicated, then it needs to have a branch to know where to send that, or it needs to be part of this. You can't have a plus and an at. Okay, if we had a preprocessor that gave us the length right off the bat first, can we do that? Swap those two around. Or like look ahead, get the length, pass that along. Like the job of this one is basically just to look ahead and get the enum and pass that along first. Or get the case and pass it along. It can't actually even do that. This 5 lines of code here, that's what chooses. That's what passes along the case. Move 2 over to X3. We do need to save the ID before we do all of this. What's this at here? So this is move accumulator over to X3. That's moving the ID over. Right, we want to move the ID over after moving the case over. And then we handle the length. We need just one more line of code here, and I can't really find a way to get that. Man, I feel like I'm just... I'm basically just golfing. So if things don't fit, I need to split off into more modules. More modules don't even like fit on the board. It'd actually be great if something like this could start off. What if there are like 2 control modules? The first one does just that, and then it hands off control to another module that is sleeping, right? So it just moves over the enum value over here, the case. And then some other module does the loop. Including some sort of pre-processing. Right? So I could have another module that's just sleeping, waiting for a signal from this module. So I'm gonna switch that back to x1. And basically, instead of loop, so we get the ID, and that gets passed along. And instead of this, okay, we're gonna duplicate this. Okay, instead of doing all this loopy stuff, which I'll save in a note here. And in fact, I could actually write this proper over here. This would be jump to loop. So we moved the signal over, like we've processed the ID. And then now we're going to move null over to x2. Right, which is going to give this thing the signal to start. But now, now I have to figure out how to wire this through into there. Well, we can slide this over a little bit. And this thing is also going to be talking to that chip. No, it's not gonna work. Okay, so this moves null over to x2. Right, this thing should never wait on x2. Like x2, its x2 is only ever gonna be output. So they'll take turns outputting there. So sleep x on x3, and then we're gonna need a big chip. I'll just move straight to a big chip. Okay. Sleep x on x3 and then move x3 to null. Okay, and then now that means it's our turn to process from our own x1. Oh, instead of we're gonna have an end here. Okay, so this handles the enum and the ID. Oh, wait, we do have to move the ID over. So our end case is actually going to be move accumulator over to x3. That's the ID. Great. So now this one, it's coming off with the packet length. So we're gonna move x1 over to accumulator. And that tells this chip here how many more we're gonna have. Also, we're gonna move that accumulator and copy that accumulator over to x2. We can do it twice. Move accumulator over to x2. So this thing gets the length twice, right? And then now we have our loop. And we just have accumulator many pieces of data to move. So we're essentially going to move x1 over to That can be its own line. Move x1 over to x2, sub 1 from our accumulator, test equal accumulator is 0. And if it's not 0 yet, then we jump back to the loop. Okay, this just moves the data over. Right? And we moved length over twice. Because the first time it's used here, it's just going to be consumed and not saved because we don't have a register in which to save it. Okay, cool. Length gets duplicated. Great. So once that is all done, we end by moving control back to the other one. So we're going to move null over x3. So this is just like extra code. So this thing is going to need to sleep on x2, and then like move x2 to null. Okay, so these two take turns. That's how we get more. That's how we get more lines of code. Okay, but that makes sense, right? I think that's reasonable. We just moved the loop over to another chip. I like it conceptually, but I'm afraid to run it. Part not sleeping, blocked on read. Move x0. Oh, this is blocked on. So the first time through, everything went fine. And we even got... Oh, how do we get -7 here? We'll step once at a time. Okay, so there's our value, and we're doing the comparison, right? And that's a 2. So that's going to the meter out. So that's already saved here. Now control should move over to this chip. Wait, are we already? Oh, that all finished like right away. Are all those sent in the same second? I guess they are sent in the same second, so we have to step through one instruction at a time. Okay. So the first thing is comparing the IDs, and it chooses to move 2 over, right? To x3. Which gets read over here as x0. And then now we're doing some branching. Nope. Actually, we did get this here. So it's like, okay, great. We'll move that out. That's the ID. And then we're subtracting from our accumulator. Right now that doesn't mean anything, but that's kind of like a generic. And then we move x0 over to accumulator. Over here, which is going to be the length. Let me make a note that that's length. Okay. So this thing moved that signal over, right? And then after that, it moves the ID over, which also gets used eventually. There we go. It gets moved over all the way to the meter out. That's good. So now we move null over to x2, which means we're going to this bottom chip. That slept, and now it's starting its own thing. So it's going to read the 4 packet length from this lower in. Great. And now we move this accumulator. We're gonna move that length over. This 4 is gonna go over to that N. Great, and it's gonna add 1 because its packet length is actually gonna be bigger, right? Because the accumulator was duplicated, it's also sending that over. So that's good. And then this is sending over length again as part of that packet for which this has the incremented accumulator. Okay. So that's running around in its loop. Cool. And that works nicely. And now we're gonna have the 81 and the 70 all go through. 81, great. The 70 goes through. 67 and 17, so 60 or 62, and the 17 goes through. Cool. So far, so good. Okay, now this should see that that's 0. This is gonna get 0 here soon. Very soon, like 2 instructions. And this is sending the signal back to this to do its wait. Meanwhile, this has ended its thing, and it's gonna go back to waiting because we've hit 0. Okay, great. So the first loop was totally fine, and let's look at the state of everything. Right, the state of everything seems fine. Like we're ready to handle another data packet, right? So now what happens the second time around? So now we're sleeping on X1 until this 301 comes in. Now the difference here is that we end up sending this 1 over. Oh, here's what happens. Oh no, we move, yeah, we move 1 over and then we jump to the end bit, right? Great, so we are in the 1 case. So that's gonna apply for all of these loops. And then we move the ID over the 301, which it uses right away, and it's sending over to the lower out. That's good. So far, so good. We're moving null over to X2. Right, we're giving this the signal to start its loop. Meanwhile, over here, what are we about to do? We're about to end up like waiting for data. Okay, and on the length, on the left, we're moving this length over twice. The first time, oh fuck. Okay, I see what's happening. So here I had this code that's blocked by an @ right? That @ doesn't reset just because it's like that's the problem, is I want it to run once per data packet. That's just gonna run once per full iteration. @ is too powerful here. So I guess I was trying to be sneaky here. Like, so we still have to handle the ID separately and then do the data packet, and then do the packet length. We're doing the packet length. Has to do something weird on the second time through the loop. So we could do the same kind of preprocessor. So this preprocessor, I suppose, Okay, so we can simplify this here. What this preprocessor could do is instead of like sending the length twice, it just sends like a full-on length to this chip, which this chip can use before it goes into its main loop, right? So let's just change that over here and see what that's going to look like. We're going to do another duplicate here. Okay, so here on the right side, we're going to move x0 to data. Then we're not initializing length here, nor here. Okay, so what we do instead, we sleep on x0, we move x0 to data, and then we're going to move x0 to accumulator. So this is our case, and this is our length. And then we just do this branching. We do this all very, very dumb. And it just loops through with those branches and with those accumulators and with those counts. Now this over here, this has done the job of like parsing the ID and then sending it over. It can't send it over yet though. So instead of move accumulator over to x3, we can move the ID over, right? We can move the ID over, or not the ID over, we can move the case over. So first we move the case over, and we can't move this ID over just yet, because this needs to run. There's gonna be this back and forth because this still has the ID. So like this moves the case over, this moves the packet length over, this moves the ID over, and then this moves all the data over. I don't know, maybe we can golf this on the top enough so that this basically sends the ID over, or the case over, and then it delegates to this to send the packet length over. And then this up here does the rest of the work. Sends all the data over, except that's not going to work because, yes, it's going to send the ID packet, it's going to send the ID over, but this thing over here has consumed the length. Oh, right, we can just pass the length over. So after we've done that pre-processing and sent it over here, we can also send it back here, right? Instead of sending null, we could send the length up here. Yes, you can put instruction on the same line as the label. So we might have to pull out that stop here, but I think that's possible. Wait, what if instead of just moving null over, we just move the ID over down here? Then this can do all the pre-processing and then also move the ID? Maybe. Okay, so what happens here, we have this x3. Geez, my worry with a problem like this is that like it's hard to follow. It's harder to follow because it's just a harder problem. It's like a harder problem for me to wrap around, which makes it harder for me to explain what I'm thinking. Whereas like the first few puzzles, you know, they're easier to follow just because they're easier puzzles. And there's like you just kind of wind your way straight to the solution rather than like backtracking. But here, okay, so this waits on null. And maybe the ID. Maybe why not? Still, we're gonna move x3 over to null. Let's just say ID. So instead of moving null over, we're gonna move accumulator over to x2. Right, so we get the ID. Case has already been sent over. And then we move x1 to the accumulator. This is the length. And we don't want to move the raw length over just yet. Because wait, why not? We're basically we're sending length. Yeah, we can just send that length over. This needs to be length plus 2 though. Move x0 over to accumulator, and then we're gonna increment it, so add 2. Is that right? Yeah, we get the case, we get the length, and then this accumulator is actually a number of data values, which is always gonna be packet length plus 2. Because we've added, because originally the first 2 were not part of the packet length, right? Yeah, so we have those 2 additional values. Okay, that works. So we're going to move x1 over to the accumulator. Right. Or, sorry, we're going to move accumulator over to x2. So we send over the length the first time. After we send over the length, now we can move the ID over. So this x3 null, we're going to move that to data instead. So move data over to x2, that's the ID. And then we need to move the length over again. Move accumulator over to x2. And then we send over the rest of the data, which is always going to be move x1 over to x2. Sub 1 from our accumulator. Test equal. And when we're all done, we move back to x3. So this thing, this at the end, all it's doing now is we move accumulator over to x2. We sleep on x2, move that to null. Cool. Oh my god. Yes. Happened. Got it. Thank you, thank you. Okay, so what did we learn here? Because this lesson definitely needs to be internalized. Not enough. Okay, there were a chunk of us that used three big chips. My power usage is atrocious, and I have a lot of lines of code, but there are like fat tails in here. The cognitive disparity, yeah. Yeah, I'm gonna have to like take this one home and think about it and learn a lesson from it. Like essentially what I did was just delegate everything else over to here, and we pre-processed the data, which means more work. That obviously means like more energy and more lines of code and an additional chip. So I think I missed how to handle the data as is. Because I did that pre-processing. But I at least learned that, well, It was good to think about, like, hey, this loop doesn't fit here, let's just move the rest of the loop over to another chip. Alright, do this blocking back and forth. I think I've done that before. It's at least a way to get it out on paper, get it working, and then you can think of improvements later. But I want to see the stats again. Yeah, my employer's happy. We can go back to the email chain. And geez, after that one, I hope they give us an easier one next. But after that one, like, I am ready for bed. Okay, what's this? 0 to 5 lines. Okay, someone's doing this just on. Someone's doing something really smart there, actually. Like usually when I see like a small number of lines of code, that tells me like, oh, maybe someone used like a ROM module or something. Um, there's probably a good chance I could reduce this by like myself just from here. But a bunch of people did it in 10. I'm sure the person who did this in like that isn't also the person that did in just one chip. So if this is 15, that's 10. Someone else did in 5, I suppose. I know, this is a you can tell this is a problem that like got people. Like some people got this problem and other people the problem got them. Oh man, I will really have to think about this because like I'm obviously missing something. Like I'll need to like take a step back altogether. It's not about making this approach better, it's about realizing I'm missing another approach altogether that was supposed to be like obvious. Um Most lines of code aren't running much. Okay, running these tests every single time, that's probably like a huge source of the energy cost. I could probably figure out a smarter way to do that. I suppose there could be a jump. Right, each of these also has a jump. That has another line of code, but removes a lot of energy. We don't have enough lines of code to do that. I suppose you can do, like here, the third test doesn't need to happen because if the second test fails, it's just that, right? Like this plus becomes, we just minus here. That's just in our else case. Else 3. Else 3, right? And that should still just work. No. Mm. Why not? So that was formerly a plus. It just became the minus of this case, right? Comment that out, make that a minus. I don't see why that wouldn't work. We are sending values to the wrong packet or the wrong output. We're like alternating. So we end up alternating between higher and lower, which is to say 1 and 3. So here's the 3 case, here's the 1 case. So if we jump through a loop, we test if it's 1, and somehow that ends up passing. I don't know. All right. I earned a sleep. Yeah. But I think it'll be satisfying to return to this and do it properly eventually. Yeah, yeah, totally. I feel the same in other Zachtronics games. It can be really satisfying. And here's the at least from my experience with TIS 100, I found like there are 3 different things you can optimize for, and it's not always going to be the same. The same code in each. So like maybe those 3, maybe minimize one like at cost of the other 2. So I wish I could kind of see that whole spread, right? Like of the solutions that were 5 lines of code, what was the cost and energy? Okay, this is just a tip of the iceberg. Mr. Sun is apparently pulling in a lot of resources and groups to create various subsystems for something. Nobody knows what it is other than it's going to be very big and potentially very lucrative for the firms involved. We're on a path to further our good relationship with his group and eventually become trusted partners. So let's continue to do our best work here. Okay. And that looks like we're back to nonsense afterwards. Or like fun stuff. Wu Lily wants just all the serious stuff from Sun. There are so many meat-based printer. Okay, there'll be some fun ones to look at. Maybe next time I should like take a sneak peek ahead of these before actually doing them. Pollution sensing window, that might be like the next Sun project. Okay. That's a night for me. I'm gonna find a stream to send off to. Oh, Howling Fantod's is on. We'll go right there. Well, good to see you. One of these days we'll get into a new project. I've been like brainstorming every now and then. I think I don't know. There's a lot of fun to be had, just not a lot of time in which to have it. But I'll be excited to get maybe one of these sessions is a digression. I'll kind of like lay out what I'm thinking. Okay, Helen and Todd's. Oh, is it just you and me? It might just be you and me. No one else has been chatting in a while anyway. Yeah, so we were rating anyway. All right, have a good night.